Hello everyone, I'm Paul and today we're solving problem 898, Bitwise OR of Subarrays. This is medium and the key for this one is observation. So let's start. We are given an integer array and we need to return the number of distinct bitwise OR of all non-empty subarrays in this array. In case you don't know what the subarray is, it's a contiguous non-empty sequence of elements within an array. So this is a subarray, this is a subarray, but we can't form a subarray with 1 and 4 because these elements are not contiguous. And in case you know what bitwise OR is, let's say we are doing 4 or 1. This is the binary representation for 4 and this is the binary representation for 1. So we are going from right to left, and each time we are comparing if at least one of the 2 bits for each position is 1. In this case we have 0 and 1, so the result for this is 1. If none of the bits is 1, for example here we have 0 and 0, the result is 0. Finally here we have 1 and 0, so the result is 1. And the base 10 representation for this number is 5. In this example we are comparing 4 and 1 and the result is greater than 4 and it's greater than 1. And this is not random. Every time we are comparing two values with bitwise OR, the result is greater or equal to the largest value we are comparing. Because think about it, we can only add bits with 1. We can never add bits with 0 to the result. For example, this bit for number 4 will never turn into a 0 because of the nature of this operator. This bit is transformed into 1 and this bit is also transformed into 1, but we can never transform 1s into 0s with this. And here we only have 3 positions, but here we have the constraints and we know that every element in the array can be smaller or equal to 10 to the power of 9. That means every number can have roughly 32 bits. So here we have 3 positions, but imagine here we have 0, 0, 0 and so on. So here we have 32 positions, 32 bits. Now we are given an array, here we have the array, and we need to find the number of distinct bitwise OR of all subarrays. And here the subarrays are 1, 2, 4, 1, 2, 1, 2, 4, and 2, 4. So we have 6 possible subarrays in this case. And the bitwise OR in this case is 1, the bitwise OR here is 2, bitwise OR is 4. Here bitwise OR is 3, here it's 7, here it's 6. And given that we have 1, 2, 3, 4, 5, 6 different bitwise OR, the result in this case is 6. Here we see the word distinct, and whenever I see this, I think about sets. So we are storing every possible bitwise OR in a set. Now the problem is, how can we get the value for every bitwise OR for every subarray? Maybe you are thinking about iterating this with 2 pointers, and by doing this you can get every possible subarray, and from this you can get every bitwise OR and add all of these into a set, and finally returning the length of the set because we need to return the number of distinct values. But the problem is here, we know that n is 5 times 10 to the power of 4, and doing that will require roughly n squared. And this is too much. We need to think about something more efficient. So we will have 2 sets, one for storing current values and the other one for the result. And we are iterating this from left to right with an I pointer, so we start here. First we have a 1, and given that this set is empty, we add the 1 here. And now we are adding the values in this set in the result, so now the result has a 1 also. So now the I pointer is here and we have a 2. And we are doing the following. We are doing 2 or each of the values in current. In this case 2 or 1. and 2 or 1 is 3. So we are replacing this with 2 or 1. So we put a 3 here. And this represents the bitwise OR of this subarray. And we also need to add the bitwise OR for the current element, which represents the result for this subarray. So we added 2 here. And now we do the same as before. We are adding this to the result. So now this is the result, this is current, and the I-pointer is here. So now we have a 4. And we are doing the same as before. We do 4 or 3, and this is 7. So we replace 3 with 7, and now we are doing 4 or 2, and this is 6. So we replace this with 6. So this 7 represents this subarray, and this 6 represents this subarray. And we need to add the value for the current subarray, so we add a 4 here. Now we are adding every value here in the result. Now we update the I-pointer, we reach the end, and we return the length of this. Given that here we have 6 elements, we return 6. Now maybe you're thinking that this is not possible because this can grow and square, but the answer is this is possible because we can have at most 32 different values here. Why? Well, because subarrays are contiguous and we are starting from one element, and from here we can only add bits with 1. And how many bits can we add? Well, we can only add 32 bits, so we can have at most 32 different values here. And this is actually not a lot, that's why we can implement this approach. So time and space complexity here will be big O of n times m, where m is 32. And remember, this represents the worst case. So now let's copy the code and hopefully you will get the idea. We are using a set for current and a set for the result. And now we are iterating every value in the array, so for x in the array. And here we have two ways to do this. We need to iterate every value in current, so for y in current. And we are taking the current x bitwise or y, and we need to store this instead of this y. And the way to do this in Python is we need to create a new set. We'll call this temp. This is an empty set, and here we are storing this x or y. And now we can add to temp the current value for the current subarray. So we add x, and now we can say current equals temp. So this is fine, this works, but I want to show you how to do this in one line. You can say current equals a new set with x or y for y in current, and we need to add x for the current subarray. So we do a new set with x, and this in Python is union for sets. So we are grouping this and these sets. And now we need to add the values in current to our set result. So we do result union equal current. And finally, we return the length of the result. So now let's submit this and see if it works. As you can see, this is efficient, and let me try this other implementation. So we comment this, and this also works, and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.